We need massive amounts of carbon-free electricity to keep civilization running without overheating the planet. It is the single most pressing engineering challenge of our time. Traditional nuclear power runs on uranium, and it carries heavy baggage. We're talking about severe meltdown risks, radioactive waste requiring safe storage for thousands of years, and the lingering threat of weapons proliferation. But there is a silvery metal hiding on the periodic table that bypasses almost all of these issues. It's called thorium, and the Earth's crust holds roughly 3 times more of it than uranium. Because of how thorium behaves at the atomic level, it produces a tiny fraction of the long-lived radioactive waste. A reactor built for this fuel cannot melt down in the way traditional plants do, and the resulting byproducts are practically useless for building a nuclear bomb. A major breakthrough proving this technology is viable just happened in Kalpakkam, India. A revolutionary new power plant there has successfully reached a crucial, highly difficult milestone known as criticality. Thorium is rapidly moving off the chalkboard and onto the power grid. To understand how this metal solves our biggest grid vulnerabilities, we have to look closely at the physics of how it actually burns. Generating nuclear energy starts with fission. You take a heavy, unstable atom and force it to split, releasing heat and fast-moving particles called neutrons. If those flying neutrons miss their targets, the chain reaction fizzles out into a subcritical state. Conversely, if those neutrons smash into too many atoms too quickly, the reaction multiplies exponentially out of control, a supercritical state. The exact stage achieved in India is criticality. It is a precise Goldilocks balance where just enough neutrons hit just enough atoms to safely sustain a continuous fire without dying out or exploding. Getting to this steady state is notoriously difficult, and thorium presents a unique hurdle. You cannot start a chain reaction with raw thorium. It simply won't burn on its own. Because the metal cannot sustain fission independently, it requires a specific reactor design to actually harvest its potential. Nuclear materials fall into 2 distinct categories. Fissile materials, like certain isotopes of uranium, can burn independently. Fertile materials, like thorium, are dormant. They need a catalyst to ignite. To solve this, engineers design a fast breeder reactor. They place a highly combustible fissile core in the center and wrap it in a thick blanket of fertile thorium. As the combustible center burns, it shoots high-energy neutrons outward. When the dormant thorium absorbs those neutrons, it undergoes an atomic transformation, turning into a highly efficient combustible fuel known as uranium-233. The reactor continuously creates new fuel out of the blanket while it burns the core. Imagine driving a car where the exhaust refines crude oil in the trunk, consistently generating a full tank of fresh gasoline. The United States actually built and tested a molten salt reactor using this exact technology at the Oak Ridge National Laboratory in Tennessee. It successfully generated power for thousands of hours in the late 1960s. The government eventually shut the project down for a specific reason. The thorium cycle does not produce the weapons-grade plutonium the military needed to stockpile nuclear warheads during the Cold War. The inability to manufacture bomb materials made thorium useless for a 20th century arms race. Today, that exact characteristic makes it the absolute safest, most peaceful option for mass civilian power. Commercializing this technology shifts the global energy map, placing a massive advantage directly in the hands of India. The country holds roughly a quarter of the world's known thorium reserves. Achieving criticality in Kalpakkam realizes a vision set decades ago by pioneering scientists like Dr. Homi Bhabha and Dr. APJ Abdul Kalam. They recognized early on that domestic thorium could permanently secure the nation's energy independence. The race to master this cycle is highly active. China is actively constructing its own thorium molten salt reactors out in the vast expanses of the Gobi Desert. Now, nations across Europe and North America are scrambling to restart their own advanced thorium programs, racing to secure supply chains and technical expertise so they aren't sidelined in the new power dynamic. While the world waits for nuclear fusion to become commercially viable in the coming decades, thorium serves as the critical bridge technology necessary to sustain surging global energy demands. Harnessing this abundant metal secures a massive volume of reliable electricity. It replaces meltdown anxiety and toxic waste with an incredibly efficient power source pulled right from the dirt beneath our feet. If you want to see who wins the race to master this centuries-long fuel source, hit that subscribe button. Let us know in the comments if you think thorium is the true answer to our grid, and we'll see you in the next one.